Got until December 18th. All right, so in this opening exercise, the very first question just states, describe the geometric effect of performing a transformation here. So remember, we had two different type of things to kind of focus on. Yesterday, we talked about dilations, which was in the form of R00R. So it's super easy to tell what the scalar factor was. This is not in that form. So in lesson 21, or what we did on Monday and Tuesday, and I even wrote it down up there, we were introduced to a new matrix of R cosine theta negative R sine theta, R sine theta, and R cosine theta. And this dealt with our dilations and rotations. But in this form here, if there's no R or no number in front of all these cosines, you can say that the R is equal to what? 1, which we know is a no dilation. So you don't have to write this part, but to understand why there isn't a dilation, that is the reason why. The big takeaway is to figure out the theta. Well, if I just look at this pattern here and I see, hey, the cosines and sines are on the same spot, what is my theta? Pi thirds, which then translates to 60 degrees. So now you have your degree of rotation. So this is a 60-degree counterclockwise rotation, which is the geometric effect there. So knowing that that's what the parent function looks like, I can dictate what I need to grab out to instantly get my answers. Now, part B tells you to do two things. It says plot 1, 0. So if you make a little graph here, 1, 0 lands right here. We'll call that, I don't know, I'll just leave it. Let's call it A, and then we'll do something else with it. So again, for the ones that weren't here, if it's written like this, remember this is the same thing as this. Both forms are the same. Okay? So that's how I was able to know exactly what to graph. Then it tells me to find what R times 1, 0. Remember, the R is this entire matrix right here. And it might be a little bit harder to tell exactly what to graph when it's written like this. So it's a little bit easier to just pull the fractions from our unit circle to get our answers. So at cosine pi thirds, I would go to pi thirds in pink and then look at the yellow, and cosine is the x value. So this just becomes 1/2 here. And obviously this will be 1/2 here. Then the sine of pi thirds, I would look at the y value, which would be the square root of 3 over 2. But here it would be negative square root 3 over 2, because that's where the negative is here. And then this would be just the square root 3 over 2. And so there's your 4 elements. And then if I multiply that to the coordinate 1, 0, remember it goes row times column to get the answer. Well, 1/2 times 1 is 1/2. And then negative square root 3 over 2 times 0 is 0. So it just goes away. So 1/2 is the first part of the element. And then do the same thing. Take the next row and multiply to that column. Thank you. And square root 3 over 2 times 1 is good. And then 1/2 times 0 is 0. So that all goes away. And so there is your new coordinate. Now, to make it a little bit easier to graph, now you might want to type these into the calculator to get decimal. So I get 0.5. And what's square root 3 over 2? Is that the 0.86 one? I think it's 0.8 something. I'm just going to go to 86 right there. And I'm only converting into decimals to kind of help me know where to graph it. So here's one right here. So 0.5 and 0.8 would roughly probably be about right here. We'll call that A prime. So yesterday we saw a dilation in which the point was in the same line and stretched out. This time, if you were to draw a degree thing, and if we were really good drawers, you could see that this actually rotated And if you're a really good drawer, you could see that it rotated 60 degrees.
It's like Z.
It does, and that was unintentional.
Oh,
Yeah, sorry. That was no, sorry. This is the chord, the line one on the
oh, I
Y,
see.
and this is an angle here. But I see the Z there. I wouldn't even thought that. But any questions there? So kind of the same process as what we did yesterday, but instead of stretching our point, now we're going to be rotating our point. Go ahead. What's polar form? Plus I sine theta. Cosine comes first. So even if you were to convert this into polar form and say 1 times cosine of 60 plus sine I of 60, you would still get the coordinate. Yes. Yeah, I'll write it back up here for you. So we had our z as rectangular form was what we use, A, B's or X and Y's? I don't forget now. I think it was, I'm just going to stick with this. X plus YI. And then in polar form, it was R times cosine of theta plus I sine of theta. So it still had it to where cosine's still first. So even if I was taking that point and rotating it, I would still get the same conclusion using that process there. Any other question? All right. So in part C here, it just says if we want to show that R has been applied twice to 1, 0, the notation would just be R squared to indicate you're going to do this rotation twice. And so I want you to find it and plot it, and then I want you to find it being rotated 3 times. Now, we kind of know what the answer should be. If I'm rotating something 60 degrees twice, how many degrees is that? 120. But if I rotate it 3 times, now it's what? 180. All right, so let's work this out. So we've already calculated this in part B, so I'm just going to start there. So this now becomes R, which remember was, well, I'll just write it like this. R times this guy, which was, you said point, I'm going to keep it as fractions. But our R, and I'm going to write it with the coordinates, was 1/2 negative square root 3 over 2, square root 3 over 2, 1/2 times this guy right here. So all I did was just re-plug in this is what the R was from part A. And this was just square root 3 over 2. Yeah. Bless you. And so now I can go through and multiply these out. So now it gets a little funner because we don't got zeros. And this again is for the R squared of 1 comma 0. This is what all this will equal. Bless you again. So take this row and multiply by this column. And it might get a little bit more complicated for you. So 1/2 times 1/2 is, go ahead. Yep. Yeah, so we did R10 in part B, and we got this answer. Sorry, this answer here. And then, but I'm wanting to find out what R squared is. So now I got to do R again by R. Yeah. And it's going to give me my R squared, and then I'm going to do it again. All right, so then 1/2 times 1/2 gives me 1/4. Negative square root 3 over 2 times the square root 3 over 2 would give me what? 3 over 4 will be negative. And then I'm going to do the same thing with this guy. Square root 3 over 2 times 1/2 would give me. And then 1/2 times square root 3 over 2 would give me. Remember, multiply fractions is straight across. So square root of 3 times 1 is square root of 3. 2 times 2 is 4. And then over here, this is 1 times square root of 3, which would just be square root of 3. And then 2 times 2, which is 4. Yeah, so with fractions, you don't have to find a common denominator. You just go straight across. In this process, you do have to find a common denominator, but it's nice because there already are. So now I can just work this out. What is a quarter minus 3/4? Okay. Negative 2/4, which is negative 1/2. Perfect, perfect. So I get negative 1/2. And then what is square root 3 over 4 plus square root 3 over 4? 2 square roots of 3 over 4, which simplifies down to just good. And we don't necessarily need the 1, but there you go right there. So that is what a second rotation is. And let's check that real quick. We know a 60-degree rotation and then another 60-degree rotation should land at 120 degrees. Is that the coordinate I just got? That's perfect. So now let's do that third rotation of 60 degrees, and we should get this as our result, because that would then be 180 degrees. So let's check it. So to do our r cubed of 10, I can just do an r times my result for the r squared. So this is this result. So that's going to be negative 1/2 square root 3 over 2. And so then again, I'm just going to replace r with what was told to me in part A. So I get 1/2 negative square root 3 over 2, square root 3 over 2 and 1/2 times what I got for my r squared, which would be negative 1/2 and square root 3 over 2. Do you all want to attempt this on your own, or do we need to work it together? I'll give you a minute to look at it at least. One half times negative 1/2. What's 1/2 times 1/2? Remember, yeah. So remember, you multiply straight across. So the two negatives would become positive, but then 1 times 1 is 1, and then 2 times 2 is 4. So think of it like this. What's half of a half? Oh, you're right. You're sure right. I don't know where I got the other. I think I was looking here. So that'd be negative, right? But then negative 1/4. Square root of 3 times square root of 3 would give you, bless you, just 3. Good. Or square root of 9 is what some students will put, and then reduce it down to 3. Negative square root 3 plus square root 3. I don't know, what is that? Yeah. Yeah, you should get the result of negative 1 comma 0. If you didn't, that's where you need to check your math, because we know a 60-degree rotation done 3 times should be 180. Bless you. I don't do that.
Just nothing.
Is 0/8 nothing? Well, it's 0,
Yeah,
but
that's
yes.
not.
Yeah, 0 on top of a fraction is 0. That's okay. But if you have 0 on the bottom, that's when we get that undefined, and that's not okay. Does teachers do that? Just say, yeah, you're dumb. No, that's this thing. It's a dumb question.
It's
That should be your final answer. Did everyone get that? All right, let's make sure we're correct. 1/2 times -1/2 gives me. Very good. Negative square root of 3/2 times square root of 3/2 would give you. Good. The square root of 3 times square root of 3 would just turn into a regular 3, and then 2 times 2 is 4. Right, and that's what I did. It's -1. It's okay. That's why we practice. We will become sufficient at fractions by the end of this course, if it not anything else. We might not remember anything about trig or something, but we will know fractions. Square root of 3 times -1 would give me perfect. And then square root of 3/2, well, I lost myself. 1/2 times the square root of 3/2, or 4. Perfect. And so if you have a -1/4 minus 3 more quarters, we now have -$1, right? If I have negative square root 3/4 plus the square root 3/4, what's going to happen here? 0. They're going to zero each other out, and I get the coordinate -1, 0, which corresponds to 180 degrees. Oh, I did too. State that first number again. What'd you get -4/8?
dude, I got
When we add when we,
negative
this part right here,
plus
okay, when we add fractions, the denominator doesn't change. Only the numerator. So this would be -1 minus 3, which I'm totally good as -4, but then it would be over 4 because the denominator won't change, which reduces down to -1. I'm good with the extra steps, but just make sure when we're adding fractions, the denominator does not change. Yes, ma'am. Yes, ma'am. Mhm. Correct.
not the way.
Maybe your brain was naturally fixing the error. Any other questions there? Or maybe just knowing what the answer should be resulted into like, all right, it has to be this. So we do all that just for practice purposes. But part D, what if I asked you to go straight to the second rotation, but I didn't want to have to find the first rotation and then find the second rotation? What if I wanted to do it all at once? Right? There's a process to that. So I don't have to do what I did in part B, then this, just to get to that coordinate. I can do it just one time and get my answer. So let me show you that process to make life easier. Hmm? No, not necessarily. It'd be nice if you could. You don't square it necessarily. But if I know I'm going to do, remember, r squared means the rotation twice. If I'm going to do the rotation twice, I can just take my original theta and just multiply it by 2. And then I instantly have my result. So what was my original theta? And if I know I'm going to apply this rotation twice, I can just take this, multiply it by 2, and what do I get? 120. So instead of having to multiply and then multiply again, I could just start up by just simply saying, hey, what's cosine of 120 degrees? Rather than having to do cosine of 60 and then do cosine of 60 again. And then this becomes the negative sine of 60, oh, sorry, 120. And then this becomes sine of 120. And this becomes cosine of 120. Because then the xy here would have been, well, technically this is the answer. You're done here, right? XY. but I want to test this to make sure it works. So what I'm going to do real quickly is I'm just going to plug in. Yeah, this is the answer right here. That's all it asks. Describe a matrix transformation that would do this. This was taken care of. So that's it. But if I wanted to make sure we were right, I would just plug in 1, 0, and let's make sure we get to the correct conclusion. So now I'm going to look at the coordinate at 120, and I see that that's going to be -1/2 here. And then it is square root 3 over 2, but that's a negative applied. So it would be the same thing. And then this would be -1/2. So this is the values at the 120-degree mark times the 1, 0. So when I work this out, -1/2 times 1 gives me just -1/2. And negative square root 3 over 2 times 0 would give me, so that washes. Then square root 3 times over 2 times 1 would give me square root 3 over 2 times 1. Perfect. And then -1/2 times 0 would be 0. So what I want you to do is this the value that we got on part C for the second rotation? Yes. And I only did it one time on multiplying. So quicker way to do it, especially if I ask you to do the rotation 4 times, you wouldn't have to want to multiply that 4 different times. That would be long in processing. So questions on this shortcut? So again, if you know how many rotations to do, just simply take your original rotation, multiply it by that value, and then you can just do the results one time. All righty, we good with that? All right, let's do some application. Let's determine how long it takes for a rotation to take, depending on your variables. So this kind of relates more to your physics. So in reality, that's really all the math you needed to know. But now to do application. Where am I going to use this in the real world, right? All right. So yeah, when you're rotating, objects in space. Huh? When you're building bridges with popsicle sticks and stuff, you want to know the degree of rotation for your drawbridge for the ships to go up and down. Yeah, this is it. This is yeah. And I always laugh because maybe back in the day, like engineers had to know this because they're like out there working stuff. But with technology, engineers go, done. This is we need this degree, this much weight support, and all this, and because the math was already done by some computer. Right. All right. Anyway, so on exercise 1 here, it says let f of t equal cosine 2t. Let g of t represent cosine of t divided by 2 and all this other stuff. Suppose f of t represents the position of a moving object that starts at 1, 0. And it's going to ask how long does it take for the object to return to its starting point. So I'm trying to find out how long does it take to go from 1, 0 back to 1, 0 when the argument of the trigonometric function changes from a t to a 2t. Bless you. And what effect does this have? So this is a simple question, looks complicated. If I want to do a full circle around back to my original point, what's the degree of rotation? 360 degrees. So let's take 360 degrees as my end result, but the inside is 2t. So how would I have to solve for t? Divide by 2. So t would equal what? 180. So when I have just a regular t, so let's say this was so we have to compare it from t to 2t. If I had a regular t and I want to go a full circle around, what would t have to equal? 360 degrees. So that means if I am doubling my time, what's that doing to the amount of time it takes to rotate? Huh? Halving it. It's taking half the time. If I double my degree rotation here, it's halving the time it takes to actually get to the finished product.
T equals 360, T equals 80.
So we are asked to find a what's the argument from the effects from t to 2t. So 2t has to equal 360. Well, if I divide by 2, 180 degree. That's right. And then t would equal 360 if I wasn't doubling it. So what is the comparison from 180 to 360? It's half a circle. So it takes half the time when theta is twice whatever t is. Mhm. Let's look at it alternatively with the t to t halves. What effect do you think is going to happen this time? If Very good. If we halved it by doubling the inside, and now we're going to half the inside, it should make sense that's going to double it. So now here we go. And we can do the math to kind of figure that out. T over 2 would equal 360 because I want to do a full circle. So then T would equal 720. Very good. So you would times it by 2 on both sides. And then T alone, again, also is 360. So what is your comparison this time? Well, half going from T halves to T, but now we're looking from T to T halves. It would be doubled in this situation. I guess really does compare to what you're looking at, but since we're going from T to T halves, it doubled the time when theta equaled T over 2. Okay. Questions? Which, if you think about it, makes sense. If you look at the previous question, if I did a 60-degree rotation and I wanted to find out twice, that would take 2 seconds. Let's say each rotation was a second long, right? It would take 2 seconds to get there. But if I was to double the 60 and one rotation get me to 120, that is now 1 second. So therefore, it took half the time when I doubled my degree of rotation. That makes sense? No? Okay. So let's look over here. If I have a coordinate, we're just going to look at 60 since that's what we did. If I look at this original coordinate here, and I just did a 6-degree rotation, and let's say each rotation took 1 second. So this would take me 1 second to get there, right? But let's say I wanted to do the rotation twice. So that'd be 60s 120 and then 180, right? So hold on. Let me back up. It would take 2 seconds, but the original point's here. Sorry, the original point's 1, 0. That's our starting spot. If I do one rotation to 60 degrees, that's 1 second. But if I double my 60 to 120, now my rotation has gotten here in 1 second because I doubled my degree of rotation. So think of it like I have a ball moving, right? And the degree of rotation is 60. Every rotation takes 1 second. So that would be 1, 2, 3, 4, 5, wherever five, then 6. So it takes 6 seconds to go in a circle. I double my rotation now. Again, each rotation takes 1 second. So now I'm going to go 120s. So now I got 1, 2, 3. Okay, if you're looking at two rotations, a 60-degree would be 12 seconds versus 120, which would only take 6 seconds. 2 seconds, right? Go ahead. Because now you're tripling it. Yes, the degree of rotation would represent a second. Hypothetically, sorry. It's going to go faster, correct. Not always. I'm just making an assumption here. The degree of rotation might take 5 seconds, but regardless if it takes 5 seconds to go 60 degrees and I doubled my degree of rotation to now 120 degrees, it will still take 5 seconds to get there because the inside has now been doubled. versus 10 seconds if the ball is moving at a slower rate. What part? Well, you're not changing. Well, you are. You're changing your speed. You're changing the speed of the rotation. How do you change? I don't. How it has to be probably more of a physics question. Maybe you have more work being done to push the degree of rotation. Maybe the object has gotten lighter. I don't know uh, I guess the circumstances behind it for a real world application. I just know if the speed has increased, my time will decrease because I'm getting there a lot faster. But what causes the degree of rotation could be a whole bunch of variables on a real world situation. Then your time decreases. That's what's happening. Yes. Okay, well, that's what I'm saying. So let's say there's two planes. Let's put a realistic sense in there, and let's say the plane's just going to make a big circle. Okay. Let's say the first plane's going, I don't know what the speed of planes go. But let's say it's going 60 miles an hour, right? And I want to get to this destination. And if I go 60 miles an hour and they take the same arc, this will take 1 hour. This will take 2 hours. I have a second plane also starting from the same airport, going 120 miles an hour, following the same arc. It will get to this destination in 1 hour. So because I doubled his speed, I got there in half the time that the other airplane did, which is what we got on the math side of it. So you increase your speed, you decrease the time it takes to get to that exact same point.
And everything you just explained, not the math. Like everything you just explained made perfect sense.
So that's the
Just
difference
not
between
math.
math and engineering. If you understood that, you're going to be an engineer. If you understand this, it's going to be math. Yeah. Yeah. But that's what's happening. If I double my degree of rotation, my time is going to be cut in half. If I cut my degree of rotation in half, it's going to double the time to get to the same point. Uh-huh. Yeah, so if it takes 10 seconds to get there, then whatever my degree of rotation times 10 would be 10 seconds to get there. But if I doubled that, then I would be um um getting there half the speed. I would get there in 5 seconds instead of 10 seconds. Yes, you double the speed, cuts the time in half. Yeah. It's that the time would still be 10, but my degree of rotation is now doubled. So I'm moving a lot faster. So I'll get there in half the time. Correct. And vice versa, we saw if we cut the speed in half, then it's going to double the time it takes me to get there.
If you don't speed,
Cut the time in half. Yes, which is what I did this math for. So you can see to get to the same spot, it was half the degree that was needed, basically you could say, and this one was double the degree needed to get to the same spot. So that affects the time, either doubles or halves, or depending on what the result is. If it's divided by three or tripled or whatever, multiply by 10 if you wanted to. Let's do some more examples. More examples always helps me. So let's look at part two. Let's put some actual degree to it. Let's say it's pi halves, which we know is just 90 degrees, times our time. All right. Part A says draw the path of P that traces the time between 0 and 1. Now, this part is going to be hard to do. Are you given a graph? No? Okay. So this is more like a Desmos thing, but I'll try my best to. Huh? It's all the time between 0 and 1. It's an infinitely many numbers. So that's what's going to be hard. But what I'm going to do is I'm just going to do 0 and 1. And then since I know it's an arc, I'm going to kind of trace it. Right? That's going to be what I try to do here in my best form. All right.
Delivery for Seville.
Uh-oh. Sorry, man. This doesn't feel good. Okay.
Thanks, Captain.
All right. Okay, so we take this right here and we're trying to map out everything from 0 to 1. So I'm going to first start off with t equals 0, and then I'll figure out what t equals 1. Right? So I'm just going to plug those values in. Now, when I plug in 0 into this guy right here, what's going to happen to all these results? It'll be 0. So at t equals 0, I would get cosine of 0 and sines of 0. Now I can use the unit circle to figure out what these points are. So I'd go to the 0 degree, and it says 1 comma 0. So that means cosine is 1 and sine would be 0. So this now becomes 1. Do I really need to say negative 0? No, I'm just going to say 0, and then 0, 1, and then 0, 1 as my matrix I'm multiplying by. So when I multiply this out, 1 times 0 is 0. And then 0 times 1 is 0. Interesting. Yes. What did I mess up on? These ones? Oh, I plugged it into the unit circle. So I went to 0 degrees, and cosine of 0 is 1, and sine of 0 is 0. But I didn't want to write a negative 0. I just wrote zeros. This 0, 1 came from right here. So now I'm going to do row times column. So 1 times 0 is 0. 0 times 1 is 0. So this just becomes 0. Then 0 times 0 is, but 1 times 1 is 1. Now, if I'm not moving, right, time has not moved because time is 0, it makes sense to have the exact same coordinate, right? Okay, cool. So this would be 0, 1. So let's say we're right here. I had to think about it. I was about to put it over here on the right. All right, so this is my starting value. We'll call this P. Okay. Which again makes sense. Time has not moved. So therefore, I should still be at 0, 1, right? Which is what my math showed. Because nothing's moved. No rotation, no dilation. Time is 0. I'm still in the same point as no work has been done, right? I don't know what it tells. Again, that's going to be a physics thing. What meat is this? Is it an airplane? Is it a train? Is it someone pushing a box? Like, I don't know. But this object hasn't moved. Now I'm going to see where does it finish? And then I can kind of guess the rest of it without having to do too much more work. So I'm going to kind of keep going here because I'm running out of room. So t equals 1 would now give me pi halves times 1. Now, if you want to go ahead, y'all do really good with degrees. So I'm going to go ahead and I'm going to change my pi halves to 90. So when I do 90 times 1, I would basically, all these guys would turn into what? 90. All right, so I'm going to rewrite it. So cosine. This one here. So you understand how I got these? So I went to the 0 degree on my unit circle, and it says the coordinate is 1 comma 0. So that means cosine is 1. So I replace cosines with 1s. And the sines is 0. So I replace the sines with 0. The 0, 1's the original point they gave me. Mhm. Because I changed pi halves to 90 degrees, and then t is now going to equal 1. So then 1 times 9. If you left it as pi halves, we're going to get the same answer. But y'all seem to work better with degrees, so I went ahead and just changed it. If you like radians, you're going to, like I said, you'll get the same conclusion because the degree in radians is going to be the same value. I'm just trying to less confuse y'all. All right, now I'm ready to simplify that original matrix. So cosine, or at 90 degrees, my coordinate is what? So that means that the cosines will turn into zeros and my sines will turn into ones. So this now becomes 0, -1, 1, 0. Now, before I do this multiplication, does everyone understand why that became -1? Because the negative was already there. Go ahead. The pi halves, then you would just get cosine of pi halves, which would still tell you it's 0. So if you keep it in radians, that's fine, but you would still take you to the same spot on the coordinate plane. Are you trying to relate this to the previous problem? So that previous problem was just asking what happens if you double the degree or double or half the degree. Okay. Oh, I'm still on A. Sorry. I just ran out of room. So I haven't done 3 seconds. On 2, t equals 0. Yeah, so I plugged in 0 for all of my t's. So 0 times pi halves would just give me 0. 0 times pi halves would give me 0. So I didn't plug in 0 here because t was equal to 0. I plugged 0 here, and I just so also happened to get 0 for those values. Now I'm plugging the t with 1, so not, and that's why I got 90. Correct. And now that I got these, I can go ahead and work these out. 0 times 0 is, and then -1 times 1 is -1. 1 times 0, 0 times 1. So there's my new coordinate. So that was me. I'll call it P prime. All right. So instead of graphing all of this between 0 and 1, the best thing to do, and I'm going to try to do this on the board, is just kind of make an arc. Ah, didn't work. Try that again. I'm making points. If you want to draw a line, that's perfectly fine. Yeah, so infinitely many points there would make an arc between 0 and 1 second. So if I wanted to know what half a second was, I'd probably be somewhere there. If I wanted to know a quarter of a second, I'd probably be there. And if I kept on changing it or doubling it, it'll be any value in between those. If you did Desmos, it does really cool and it actually kind of plots it as it moves in time, depending on what value you want. But that's kind of hard to do. Okay. So that is plotting all the points between 0 and 1. So then part B, go ahead and find out where would this object be in 3 seconds. Yeah, do part B, and you're going to find out where does the object fall in 3 seconds. Correct. Whoa. What ones are you replacing? These? These. Yes, yes. Okay. At first, I thought you were doing, no, that's not necessarily, it's going to work out. Go ahead. Oh, I changed pi halves to 9 degrees from here, from the original problem. Times 3. There you go. Yeah. Or X or Y. Or X or Y. Yeah. A or B. Yeah. Correct. Same question. Because it becomes a negative one, which is positive. Yep. You already finished part B? Perfect. Yes. Yeah. That's right. Yeah. The cosine will represent the x value of the coordinate, and the sine will equal to here. So I went to 90 degrees, and I look at the yellow coordinates. So I'll go to this one. So anywhere there's a cosine will now be a zero. The whole thing will return. Anywhere there's a sine will now be a negative one. But what Jacob and Kayla were both saying is because it's already negative sine, then it becomes a negative one, which then turns into a positive one. Oh, okay. This is a good place to stop then.